We are extending what we did in the last section. In the last section, we graphed these linear inequalities and we found the vertices of an enclosed region. And so now we're going to take that and do something else called optimization. So just a little bit of vocabulary first of all. The feasible region is enclosed or bounded by the constraints. So the lines that we graph are called the constraints. We refer to them sometimes as boundary lines, but those are the constraints, and the region enclosed is the bounded area. And so then this is called the feasible region. The maximum or minimum value of a related function always will occur at a vertex of the feasible region. So we're going to be enclosing, in some cases, sometimes we have an unbounded region, like this situation. And in that case, the feasible region is open and can go on forever. It is unbounded. Unbounded regions have either a maximum or a minimum. So for this particular one, there would be a maximum and it would occur at one of these 2 points, but the minimum, there is none. Now, this doesn't necessarily mean that this point right here is the maximum because it's the highest, because we're going to be given another function and we're going to be testing these values. You'll see that in just a minute. So let's go through some examples. We're going to graph the following system of inequalities. That's not new. You've done that before. Then we're going to name the coordinates of the vertices of the feasible region. That's not new either. You've named the vertices of a region. And then we're going to find the maximum and minimum values of a function. Now this looks a little different because it's a function in 2 variables. So we would say this, f of x, y equals 3x minus 2y. So we're going to find the maximum and minimum values of that particular function. So I'm going to start with my boundary line x equals 5, and recall that this is a vertical line. Remember, if we have y equals a constant, it's horizontal. And then you can either, I'm going to use the x and y intercepts to graph this one. So x equals 5 is my boundary line. Notice that none of them are shaded, or none of them are dashed. They're all they're all solid lines. So I'm going to graph the line x equals 5, the vertical line. So I get this, counting by ones. And my horizontal line passes through 4. And I guess I should be thinking about this, the inequality portion of this. This is less than, so I want the values that are less than, which puts me on this side. This is also less than, so it puts me on this side of the line. And then for the last one, if I let x equal 0, I get y is 2. And if I let y equal 0, I get x is 2. And that means I'm also using the idea of slope to find a few more points. And then we can graph those. And this one, if I test 0, 0, since it's not solved for y, 0 is greater than or equal to 2 is false. So I don't want the side that has 0, 0, so I want this side. So my feasible region is just this triangle. Now, nothing new yet. So far we've done this before. All right, so now I have to name the coordinates of the vertices. So the feasible region is this triangular region that I have. Now I need the coordinates of the vertices, and it's pretty easy to tell. -2, 4, because I can see right where they are, which is why graph paper is good. 5, 4, some of you, when you're doing it on your own lined paper, it's kind of hard to tell where they cross. And then this, we have 5, -3. Okay, those are my vertices. Now we've got this function, this f of x, y. So what we're going to do is we're going to take our values that we got for our vertices and we're going to plug them in for x and y, and we're going to see which one gives us the largest value. So I'm going to make a little table. I'm going to have x, y, and f of xy. So if we could have negative 2, 4, 5, 4, or 5, negative 3. So here I'm going to do 3 times negative 2 plus up, no. So 3 times negative 2 minus 2 times 4. So I get negative 6 minus 8, so we get negative 14. Here we're going to have 3 times 5 minus 2 times 4. So I get 15 minus 8, which is 7. And here we have 3 times 5 minus 2 times negative 3. So we get 15 plus 6, be careful there, is 21. Now, I'm asked to find the maximum and minimum values of the function. So the maximum value is 21. And the minimum value is negative 14, because that would be the lowest. You're just literally looking for the largest value and the smallest value of the function that they give you. So we're guaranteed that, that any of these other points, like if I were to plug in another point that's in the feasible region, it will not be a max or a min, because the maxes and mins always occur at the vertices of the feasible region. So those are the only points that we have to test. So here is a problem for you to try. Do it neatly on your paper. It is very much like the one I just did. This boundary line here is going to be a vertical line. This boundary, y equals 5, is going to be, because the boundary line is just an equation, so y equals 5 is what you're going to graph. That's a horizontal line. And this one you can use with x and y intercepts if you want, but you're going to graph this. You're going to find the vertices, substitute them into the function just like I did, and state what the maximum and what the minimum is. So when you upload your notes, I'm going to be checking to see that you did this problem. So make sure that you do a good job on that. All right, so for this next problem, you can see from the title right here that we're going to be looking at an unbounded region. So we're going to see how we deal with one of those. I'm going to use the x and y intercepts method to graph this. So if I let x equal 0, then this covers up. Okay, if I let x equal 0, then I'm going to get y equals 1. If I let y equal 0, then x would have to be negative 2. Now, once I plot those 2 points, I could go get, well, I can get a tool to make a line. You could get a ruler, but notice that this, even without solving this, I can see the slope must be 1/2 because up 1 over, just from using my x and y intercepts. So I could plot a few more points using the slope that I just found to be true, and then I could graph my line. And if you test a point 0, 0, you're going to get 0 less than or equal to 2, which is true, which means I'm on this side. Okay, for the next one, I'm also going to use, I think I'll do different colors for you, so when you look back, you can see which one's which, if you look back. So if I let x equal 0, then I'm going to get y equals negative 2. And if y equals 0, I get x equals 4. Okay, so I'm going to put, actually the slope is positive, is 1/2 again. So I'm going to fill in some points and draw my line. So on this one, if I test 0, 0, I get 0 is less than or equal to 4, which is true. So I want to be on the side that contains 0, 0, which is this side. And the last one, if I let x equal 0, I get y is negative 2. And if I let y equal 0, I get x is negative 2. And and the slope I can see is a -1, so I'll put a few more points on there so I can get a good line. So there's my line, and if I test 0, 0, I'm going to get 0 is greater than or equal to -2, which is true. So I need this portion here. So my region is this here. Now notice it's unbounded. It keeps going. It's going to keep extending in that direction. So, oops, lots of things to click here. So this is unbounded, and I still need to find the maximum and minimum value of the function, and I'm still guaranteed that it happens at the vertices. So when I take a look at my function, so I'm going to, I only have 2 vertices this time that are in that region. So I have 0, -2, and -2, 0 are my vertices. So I'm going to have x, y, and f of xy. So my choices are -2, 0, and 0, -2. Using my function here, I'm going to take 2 times -2 plus 3 times 0. So I get -4. And here I'm going to take 2 times 0 plus 3 times -2. And I get -6. So I have a minimum of -6, because that's the lower one. And there is no maximum because of this, because it's unbounded when you go in that direction. So there's only going to be a minimum, but no maximum. So you have a problem to try. So you're going to go ahead and graph this. Hopefully you have graph paper that you're doing this on. And as you go through these examples, then you're going to, okay, I think I gave you the graph paper to use to do this. So you should be able to do this no problem. So go ahead, and I'll be looking to see when you upload your notes that you have done this and done that correctly. So use this previous problem as an example when you do that.